Okay, so let's start. Let's start. So, for those who wants to follow the textbook, um, we are at the page 9. So it makes it easier for you to follow in the textbook, also for instructions or your own reading. Okay. So we will go into mathematical formulation for what we said about the histograms and the distributions based on different hypotheses. Okay, so um, okay, so uh, here we take a, a, a sample, one sample W0, and that W0 has a, variance and standard deviation. Sorry, has a standard deviation. And then if we write the probability density function, right? We write the probability density function is going to be something like this, right? Uh, it's a Gaussian distribution. Gaussian distribution uh, with square root 2 pi sigma square is back of parenthesis minus 1 over 2 sigma square W0. So this is a Gaussian distribution, a Gaussian distribution. Okay, and it's illustrated in figure 1.5 and figure 1.4. So let's take a look again. If you see it flat, it looks like that. It looks like that. And then if you see uh, larger variance, it looks like that. But histogram is like this. So you can imagine this is something like that, and this is something like that. Yeah, it's actually a distribution kind of thing. Distribution, and you have two distributions here too. Okay. Okay. So let's go back to the formula. So the performance of any detector will depend on how different the PDF are under each hypothesis. So for the same example, for the same example, we plot the PDF as given by this for this and that. When noise only is present, there are something like that, right? Noise only. Uh, Remember that this is a Gaussian distribution. Okay, this is a Gaussian distribution. Gaussian distribution, except that the variance is different. So when a signal is embedded in noise, recall that the keyword signal. You have a signal. What signal? What signal? This signal, one. And this signal, one. So if you have a signal embedded in noise, the PDF are like this. It may not look that simple at the first when you first see it, it may not be that simple. But if we see it this way, this is a Gaussian. We have no problem with that. This is what? This is a Gaussian with a mean equal to one, right? It's a mean equal to one. Recall that the Gaussian distribution at the exponent part, it has this x minus mu square, right? X minus mu square at where? At this exponent, right? That's the Gaussian distribution. And this mu is the mean. So this is the mean, and this is the mean. Okay? And the variance is represented by coefficients in the denominator. Okay? We will see later that the detection performance improves as the distance between the PDF increases or as a square over sigma square increases. This is oftentimes called SNR. SNR. This example illustrates the basic result that the detection performance depends on the discrimination between the two hypotheses, or equivalently, the two PDF. More formally, we model a previous detection problem as one of choosing between H0 and H1. So the problem is actually choosing between two hypotheses, H0 and H1. H0 is the noise only, 1 is the signal present hypothesis. So this is H0 and H1. The PDF under each hypothesis are denoted by this condition on H0, what is the probability of X0? Condition on H1, what is the probability of X0? Which in this example are something like that, something like that. So H0, X0, H1, X1. So that is the distribution, probability density distribution, PDF. Note that in deciding between H0 and H1, we are essentially asking whether X0 has been generated according to this or to that. Alternatively, if we consider the family of PDFs, the family of PDF, that is P of X0 condition on A, that's the whole family because A can be very different. It could be 0, 1, 2, 3, 4, up to a lot of different possibilities, right? So we call it a family of PDF. Okay, so let's see the PDF from the perspective of PDF for signal present and signal absent. So this is uh, the noise only, noise only. So it's distributed this way, and then it's signal only, and then it's distributed this way, and it's noise only. It's signal plus noise with different kind of variance, different kind of variance. So you see that it's distributed very differently in this case. But in this case, you see a lot of overlap, right? This area, the overlap. So we want to emphasize that the overlap is the area that gives us errors because when you receive signals along this area, it will be very difficult for you to determine whether it's H0 or H1 because it could be both, right? It could be one of them with reasonably high probability. So that is the family. We talk about family. The family of PDF is parameterized by A. So it's parameterized by A. Then we obtain this P of X0 condition on H0 if A is 0, and P of X0 H1 if A is 1. We may therefore view the detection problem as a parameter test. Given the observation whose PDF is given by that, we want to test if A is 0 or A is 1. Okay? So hypothesis, symbolically, hypothesis 0 is A equal to 0, or H1 is, which is A equal to 1. This is turn a parameter test of a PDF. At times, it is convenient to assign prior probability to the possible occurrence of H0 and H1. For example, in some digital communication systems, a 0 and 1 with amplitude A equal to 1, the corresponding hypothesis is given by that. Okay, this is like a BPSK, the same similar stuff. Okay, so the data bits 0 and 1 are equally likely, meaning that the prior probability of 0 and 1 are 0.5. So equally likely to be generated by the source. We would expect H0 to be true half the time, H1 the other half. It makes sense when then in regard to hypothesis, random events with probability half. In other words, uh, hypotheses H0 and H1 are equally likely in terms of their prior probability. But if they are unequal, then um, then we have to take prior probability into consideration, and that's called Bayesian. That's called Bayesian. Bayesian approach. And we have a small chapter later to talk about Bayesian, but it's equally likely for now. Okay, so the probability distribution is like this, and the probability distribution is like that. And whenever you receive a data, you are trying to distinguish between the two. So that's a binary hypothesis test problem. Okay, and then the detection problem we'll proceed from the simplest. This is a simple one to a more difficult. So we need to be careful and also be aware that a lot of things here are idealized. They're idealized. You have two hypotheses and they are Gaussian. Those things are ideal case. We could have different kind of PDF. For example, if they are not Gaussian, right? They could be non-Gaussian, right? And also uh, mathematical tractability. Gaussian distribution is mathematically tractable. A lot of things may not be, right? Non-Gaussian distribution. So if for mathematical tractability, the Gaussian PDF is particularly convenient from the theoretical and practical point of view, and will be the assumption most often made. So the Gaussian PDF is replaced by a more general non-Gaussian. In some cases, it will be replaced by non-Gaussian. Okay, so if we look at the type of problems, we will see the thing that we look again. We have hypothesis that is zero mean, and this is one as a mean, and it's Gaussian, and the statistics, which is the mean and variance, are known, right? All those are assumptions. Okay, so this is the Gaussian non-PDF case. That is the most simple case, and it could have Gaussian and unknown. What do we mean by unknown? The sigma square may not be known, right? The sigma square, for no reason should we assume that we know sigma square, right? For no reason. So it could be unknown, and non-Gaussian and known, or non-Gaussian and unknown, or different kind of combinations. And the signal power, for signal power, what do we mean by signal here? It's zero, no signal, or one as the signal, right? This is a signal. Can the signal be deterministic and known? Yes, that's what we do here. That's what we do here. But it can be other types of signal: deterministic unknown, random known, or random unknown, right? Random unknown is the most difficult, right? You have a random signal and you don't know anything about it. You maybe you know part of it, but not all of it. So that's a random and unknown. And random and known meaning maybe you have a chi-square, you have a Rayleigh distribution, you have a Rayleigh distribution, but you don't know much about the statistics. For example, the variance you don't know, right? And it could be deterministic and unknown, right? Some uh, some communication systems, you know the signal is deterministic, but you don't know the statistics. You don't know the, I'm sorry, you know it's deterministic, but you don't know about the waveform. Okay, so that's the deterministic unknown. So you have all kinds of combinations. So we need to be aware and get ready for that. Okay, I think that's the end of chapter 1. So next time we are going to continue to chapter 2.